Welcome back for another deep dive. Today we're going to be tackling something that might sound a little bit intimidating at first, but bear with me because it's incredibly cool and it's actually really relevant to your life.
Mhm.
We're talking about predicting the unpredictable, and the tool we're using to do this is called, get this, temporal graph neural networks for irregular data.
Quite a mouthful.
It is. Thankfully, there's an acronym for it, TGNN4I. So much easier. But before we get lost in the alphabet soup, I think it would be helpful to get a high-level overview, don't you?
Absolutely. Imagine for a second you're trying to predict traffic flow, right? But some of your traffic sensors are down, or
Hmm.
maybe you're trying to model weather patterns, but there are gaps in your historical data. These are exactly the kinds of challenges that TGNN4I is designed to tackle.
Okay, so it's like trying to solve a jigsaw puzzle with some pieces missing.
Yeah, that's a great analogy. And the thing is, this type of scenario is actually really common in the real world. Think about systems like social networks or disease spread or even financial markets. All of these can be represented as graphs with data that changes over time,
Mm.
right? What we call temporal graph data.
Right, right.
The problem is traditional forecasting models, they really struggle when the timing of that data is off,
Yeah.
like if it's inconsistent or if they're missing values.
Yeah, it makes sense. The old models kind of expect everything to arrive right on schedule, neatly packaged.
Exactly. But TGNN4I, this is where things get interesting. TGNN4I is based on this really cool concept called a time-continuous latent state. It's like imagining that each point on the graph has its own little internal clock that's constantly running, even when we don't have new data coming in.
So it's like the model is constantly filling in the gaps, even when information is missing.
Yeah, that's a great way to put it. And the way it achieves this is through a really clever combination of three components. Ordinary differential equations, ODEs, those are a mouthful gated recurrent units, GRUs, and graph neural networks, GNNs. That's a lot of jargon, I know, but together, this powerful trio allows the model to not only understand the flow of time, but also those complex relationships within the system.
Okay, I have to admit, I'm starting to feel a little bit lost in all the technical terms. Can we maybe break down each of those components a little bit more and explain why they're so groundbreaking?
Of course, of course. Let's start with ODEs. You can kind of think of them as the engine that keeps the model's internal clock ticking even between data points.
Hmm.
So even when we don't have observations, they allow the model to sort of, make assumptions about how the system might be changing.
So it's like the model is making educated guesses about what's happening behind the scenes.
Precisely. Then we have the GRUs, and these act like the model's memory. So whenever new data does come in, the GRUs use that new data to update the model's understanding of the system, taking into account both the new information but also everything it's learned in the past.
So the GRUs are making sure the model learns from its experiences.
You got it. And finally, we have the GNNs, and these are like the communicators. So they allow each node in the graph to actually share information with its neighbors.
Oh, okay.
This is super important because it means the model isn't just looking at individual data points in isolation, but it's understanding how those data points actually fit together as part of a larger system.
So it's like each part of the system is whispering secrets to the others, trying to piece together what's going on.
I love that analogy. It really captures the essence of what makes TGNF4I so innovative. It's this ability to learn from this real-world data that's messy and unpredictable in a way that traditional models just couldn't.
This is honestly where I usually start to get lost with AI. All the cool stuff is happening under the hood, but it's hard to grasp the actual practical impact. Can we maybe dive into a specific example to see how these components actually work together, like in action?
Absolutely. Let's go back to that traffic sensor example.
Yeah.
Okay. So imagine we have a sensor that's measuring the traffic flow on a busy highway,
Hmm.
and then suddenly that sensor goes offline for a couple of hours. What happens?
Well, in my experience, I guess it throws a digital tantrum.
Well, not quite. But this is where the real magic of ODEs comes in, right? Remember, they control that time-continuous aspect of the model.
Mm-hmm.
So even though the sensor is offline, the model's internal clock, it's still running. The ODEs kick in, they start to make predictions about how the traffic flow is likely changing based on past patterns and what other sensors are saying.
So it's like the model is saying, okay, I haven't heard from the sensor in a while, but based on what I know about traffic and what other sensors are telling me, I think this is what's happening.
Exactly, exactly. And there are two main ways that those ODEs actually make predictions. One is called exponential decay, and the other is periodic dynamics.
Okay.
Exponential decay is kind of like a fading memory.
Right.
So information from older observations gradually becomes less important as
Yeah.
time goes by.
Okay. So The further back in time something happened, the less weight it carries in the current prediction.
Right, right. But then there's also periodic dynamics, right? And this is where the model can actually anticipate patterns that repeat over time.
Okay.
Think about things like rush hour traffic or seasonal changes in the weather. The model can learn these cycles and factor them into its predictions, even when data is missing.
So it's like the model is saying, even though I don't have data for 5 p.m. today, I know that traffic usually peaks around then, so I'm going to include that in my prediction.
Exactly. You got it. And what's really neat is that TGNN4i doesn't just blindly apply one of those dynamics or the other. It actually looks at the data and figures out which approach makes more sense for a given situation.
So it's actually adapting its strategy based on what it's learning.
Exactly. It's like a master detective piecing together clues from all the available evidence to come up with the most accurate prediction possible.
This is way cooler than I thought it would be. But how do we know if the model is actually any good at making these predictions? Like, how do you test something this complex?
That is a great question, and that's what we'll be covering in the next part of our deep dive.
All right, so we've got this model that can make these predictions even when data is missing. But how do we actually know if it's any good? How do you test something as complex as TGN and 4i?
Yeah, testing is super important with any AI model, right? You got to make sure it actually lives up to all the hype.
Right.
And in their paper, they really put TGN and 4i through the ringer using 3 main data sets.
So they basically just threw a bunch of data at it and saw what happened.
Well, it was a little more strategic than that. Each data set was chosen to showcase different aspects of what the model could do.
Okay.
They used real-world data, simulated data, just to really push the model to its limits. Let's start with the traffic data. Okay. So they used traffic speed recordings from highways in California, the PM's Bay, and Meteorlay data sets. And to make things even more challenging, they actually intentionally introduced gaps and irregularities into the data.
So they basically created like the worst case scenario, missing data, inconsistent timing, all that stuff.
Exactly. They wanted to see if TGNFRI could still make accurate predictions even under those conditions.
And did it pass the test?
It did. It was able to accurately predict the traffic flow, even with all those missing pieces of the puzzle. It's really one of its key strengths. It's robust to that messy, unpredictable nature of real-world data.
That's pretty impressive.
Then they moved on to climate data, which is another great example where traditional models often struggle. They used a data set called USHCN, and it has daily temperature readings from all across the United States.
That sounds like a lot of data to process.
It is. And it's also very sparse, meaning there are a lot of gaps in those historical records. And the sheer scale of it, it presents a real challenge for traditional forecasting models.
So how did TGNN4i fare in this climate change showdown?
It did really well. It was able to accurately predict those temperature trends over time, even with those gaps and inconsistencies. It's pretty exciting because it suggests that TGN4i could be a valuable tool for understanding and predicting the impacts of climate change.
That's really cool. Okay, so it can handle messy real-world data, but what about that periodic dynamic stuff we were talking about earlier? How did they test that?
Right, good question. So for that, they actually created a synthetic data set. It had these simulated signals propagating through a graph. You can kind of think of it like a ripple effect spreading across a network.
Like how information spreads on social media or how trends catch on in different regions?
Yeah, exactly. Perfect analogy. And this test was all about seeing if TGNN4i could accurately predict those recurring patterns.
Okay. And drum roll, please. Did it nail it?
It did. The model was able to learn those periodic dynamics and make these really accurate predictions about how those signals would spread through the graph. It was like it could see the future.
That's amazing. But let's be honest, researchers always love comparing their new shiny models to the old standbys. So did they pit TGNN4i against any other models to see how it stacked up?
Of course they did. They compared TGNN4i to several other state-of-the-art forecasting models, including some big names like GRUD, even the famous Transformer model.
Wow, okay, so it was like a forecasting battle royale.
You could say that.
Yeah.
And in almost every case, TGNN4i came out on top. It consistently outperformed the other models, especially when you were dealing with that sparse or irregular data. It just really highlights the power of combining those 3 key ingredients: the ODEs, the GRUs, and the GNNs.
It's not just one magic ingredient, it's the whole recipe that makes it so effective.
Exactly. It's like a perfectly balanced recipe where each ingredient plays a role in creating that delicious final product.
I like that.
But as with any complex recipe, there's always some tweaking and fine-tuning involved, right?
You're talking about that hyperparameter tuning stuff, right? Isn't that where it gets super technical?
It can be. But it's really an essential part of getting the best performance out of any machine learning model.
Mm.
Think of it like fine-tuning the engine of a race car. You need to adjust all those settings to get the most speed and efficiency.
So they basically just experimented with different configurations to see what worked best for each data set.
Right. And by carefully tuning those parameters, they were able to squeeze out even more performance from TGN and 4i.
I see.
But enough about all the technical stuff. Let's talk about what this all means for the real world.
Yes. We've established this model is a forecasting superstar. But where can we actually use this thing, like real-world
Oh,
examples?
the potential applications are huge.
Yeah.
Let's start with transportation, right? Imagine a world where traffic just flowed smoothly. No more soul-crushing rush hour jams.
Oh, yes, please.
TGN4i could be used to predict and manage that traffic flow in real time, dynamically adjusting traffic signals, suggesting alternative routes, all to keep things moving.
So it's like having a super intelligent traffic conductor orchestrating everything behind the scenes. I love that, especially for someone who hates traffic as much as I do. What about other areas? Where else could we apply this?
Oh, absolutely. Another really promising area is climate modeling. We've talked about how TGNN4i can handle all that large-scale climate data, but think about the implications. We could use it to predict those extreme weather events, to model the effects of climate change, even inform those strategies for mitigating those effects.
Wow, that's huge. It could really help us tackle one of the biggest challenges facing humanity.
It really could.
You know what? Something's been bugging me, though. We've been talking a lot about predicting things, but what about preventing them? Could TGN N4I be used to actually stop problems before they even happen?
That's a really fascinating question, and it gets to the heart of what makes TGNN4i so exciting. It's not just about predicting the future, right? It's about understanding how things work so well that we can start to shape them for the better. And that's something we can explore further in the last part of our deep dive.
We've spent this deep dive really getting into the nitty-gritty of TGN N4I, and it's been mind-blowing, to say the least. But now I'm curious, what's next for this technology? What are researchers working on, and where could all of this lead?
It's exciting to think about, right? One area where researchers are really pushing the boundaries is dealing with dynamic graphs.
Hmm.
So, so far we've been talking about systems where the connections between things are relatively stable.
Like the connections between points in a traffic network, you mean?
Exactly, exactly. But what happens when those connections are constantly changing? Think about social networks where people are making new friends all the time, or financial markets where you have all these mergers and splits happening.
Okay, yeah.
That means the model needs to be able to adapt to a network that's literally shifting under its feet, right?
Right. It's got to keep up with all that change.
Exactly. And researchers are currently working on ways to incorporate that kind of dynamic graph structure directly into the model, which would allow it to make accurate predictions even as the network is evolving.
That sounds insanely complex.
It is. It's a really challenging problem. But another really fascinating area is this idea of combining TGNN4i with other types of AI. So, imagine if you could integrate it with natural language processing.
Oh, wow.
So the model could actually understand text from social media or news articles, or even combine it with computer vision to analyze images and videos.
So instead of just relying on numbers, the model could process information more like a human would, like taking in words, images, and really understanding that bigger picture.
Precisely. And by bringing all those different data sources together, we could get this much richer understanding of how complex systems work and make even better predictions.
That's like giving the model superpowers. But honestly, this all sounds super advanced. Will this technology ever be something that everyday people can actually use, or will it always be in the hands of researchers and tech wizards?
Yeah, that's a great question. And accessibility is definitely something the AI community is increasingly focused on.
Hmm.
We already see the development of all these more user-friendly tools and platforms. And that makes it easier for people who may not have that deep technical expertise
Yeah.
to actually use these powerful models.
So you're saying that one day we could all be using TGNN4I to solve problems in our own lives?
Absolutely. Imagine being able to use it to optimize your daily commute, or to predict trends in your industry, or even personalize your healthcare. The possibilities really are endless.
That's a future I'm definitely on board with. But before we wrap things up, I gotta ask, what are you personally most excited about when it comes to the future of TGNN4I? Like, what gets you out of bed in the morning?
What really excites me is the potential for TGNN4i to help us solve some of the world's biggest challenges. We've talked about traffic, we've talked about climate change, but what about predicting and preventing disease outbreaks? or optimizing energy grids, or even understanding and mitigating social inequality.
Wow, that's inspiring. So it's like this technology has the potential to not just predict the future, but to actually make it a better place.
That's the dream, isn't it? To use what we know and the tools we have to create a brighter future for everyone. And I really believe that TGNN4I and AI in general can play a huge role in making that dream a reality.
Well, I think it's safe to say we've covered a lot of ground today. We've gone from like the nuts and bolts of how TGN-N4I works to its potential to really transform the world. I don't know about you, but I'm feeling pretty optimistic about the future.
Me too. And I hope our listeners are feeling inspired to learn more about this amazing field and all the possibilities that it holds.
Absolutely. If you're as intrigued by TGN-N4I as we are, we encourage you to dig deeper, explore the research, and imagine how this technology could shape your own world. And until next time, keep exploring, keep questioning, and keep that curiosity burning bright.
It's been great diving deep with you.